let's look down here at number 7. It says find the component form of the vector that translates the point P 2, -5 to P prime 5, -10. So we are asking ourselves, how did this point 2 become the point 5? How did the point 2 become the point 5? Well, we added 3. It's 5 plus what? Oh, I went backwards. I'm trying to get 5 as the result. 2 plus what is 5? So we can absolutely do algebra and find that value if we need to. We can absolutely use algebra to get that. Then I can do the same thing for finding the vertical component. How does -5 become -10? So how does -5 become -10? So let's add 5. Well, we subtracted 5 is what it says. So here is the component form of the vector that takes us from our pre-image to our image. Now's a great time to ask questions if you're confused how to find the vector given a point from the pre-image and the image. Example 8 requires us to move to the side just a little bit and write a definition before we can actually do the example. So I'm going to make a little asterisk, not in a highlighter, make a little note for myself. So I'm going to use an asterisk to do that. So what we need to know is how to write the rule form. So far, we've been using component form. That's what this form with those pointy parentheses was. So rule form is going to look like this. We say, here's this ordered pair xy. This will always stay xy. It will never change. With an arrow following it, it says xy becomes the point x plus or minus a number, comma y plus or minus some number. So this is the form it's going to take on. The only thing you will ever change about this equation is the number that goes right here and its sign. That's the only piece of rule form that will ever change. That non-highlighted notation, x and y, will always be there. So you can start a question when it asks you for the rule form of a translation. You can just write that info and then go to your picture to fill in those highlighted spaces. So that's exactly what I'm going to show you here on number 8. So it says I need rule form, so that means I always start with the coordinate xy becomes, and we're going to have an x, something's going to happen to it, and then a y. So now our job is to find out, how is the x changing, how is the y changing? What's the horizontal change, what's the vertical change? So I'm going to go over to our graph now, and I'm going to enlarge it so we can see all the notation. You'll notice that the blue figure is made up of the points A, B, C, while the red figure is made up of the points A prime, B prime, C prime. So another way I help myself remember this is the blue is pre-image with a P, the red is the image with an I. So pre-image becomes image. So I'm going to pick one point. I've got to figure out how this changed. How did the blue triangle become red? So I'm going to follow just this point A, and I'm going to find out how did it become the point A prime. So I'm going to use my bunny hops. We went left, so -1, -2, -3, -4. So I'm going to write that here. I went left 4 in words. We went left 4. I'm going to zoom back in. We're going to find out what happened to the y. And then we went up 1. So we added 1. Went up 1. Okay, so writing a rule, you can see here from this example number 8, we always use that dark blue. We always set up rule form with the coordinate xy becomes is the arrow. And then we set up our new ordered pairs. We have our x and y, and then we count our horizontal and vertical change to fill in the rest of that rule form. Now we're going to get into some slightly trickier. We're going to use the rule form here on number 9. So here is our pre-image. This is the pre-image. Point S has the coordinate 5, 2. And then we're going to translate it using the rule form of xy becomes x plus 1, y plus 2. So I'm literally going to take my ordered pair, and I'm going to plug this 5 in right there in my rule form to find the new x-coordinate of the image. And then I'm going to do it again, but with my y. I'm going to plug my original y-coordinate from my pre-image into the rule form to find the y-coordinate of the image. So we'll have 5 plus 1, comma, 2 plus 2. That's what S prime will be. That's our image. I simplify, and I find that S prime has a value of 6, 4. Our image S prime is at the point 6, 4. Our last example today has us use the translation in rule form, and it's going to ask us to go backwards. It gives us our rule and then asks us to find the pre-image if we already know the image. So here's how I go about doing this. If I know the rule and I know what it gave me, I'm going to set those equal. So x plus 1 equals 0. And when I solve that, I'm going to find out what exactly did I plug in the first place. And then separately, I'll do that for my y's. They gave me the rule, and I know it gave me -5, so I'm going to set those equal. Y plus 2 equals -5. I'm going to solve each of those, and together, I'll be able to find the pre-image R. So if you need a moment to pause and do your algebra, do so now. Subtract 1 from both sides with my x, and I get -1. Move to my y's, I subtract 2 from both sides, and I get -7. I put those together, and I find the pre-image point R had a coordinate of -1, -7.
Now let's talk about translation as rigid motion. This idea of rigid motion helps us understand what happens to a figure when it is translated.
The first part we're going to start with is the postulate, 4.1. Don't memorize that. Naming postulates with their numbers is specific to a textbook, so that'll change if you look at a different textbook. What you need to know is that it's called the translation postulate. And that postulate says that a translation is a rigid motion. A rigid motion. That's another important vocab word this chapter. So if it's in a postulate, we've got to know what it means. So a rigid motion, let's define that then. A rigid motion is a transformation that preserves length and angle measure. Preserves is a tricky word. Preserves means it keeps it. It keeps it. It keeps the length and angle measures. Keeps the length and angle measures. Another name you might want to be familiar with is that a rigid motion can also be called an isometry. That's an ACT level word. A rigid motion is also called an isometry. And what's really important about rigid motions, isometries, is that it keeps lines as lines. Rays become rays, segments to segments. So we're not changing shapes. This triangle doesn't magically become a rectangle, or a point doesn't magically become a line. So everything about the figure, all its lengths on the side, all the angle measures inside it, all of those pieces are kept equal as we translate figures. So here in example 11, it says a translation maps the figure on the left to the figure on the right. So I'm going to use that trick from yesterday where I write P and I inside the figure for pre-image and image. So the figure on the left is the pre-image, becomes the figure on the right image. Okay, so now I can see red became blue. I use P for pre-image, I for image. So we need to find the value of the variables in this shape. So I see 4 variables to find. So I'm going to start at the top. So what I see right away is this 162 degrees. I'm going to match it with its exact angle in the image, which we can see is that 3W. I'm going to set those two pieces equal to each other. 162 equals 3W. And that's how I'm going to find the value of W. I'm going to use some algebra. So here I just have to divide both sides by 3. And I find W has a value of 54. Let's do some more. I'm going to change color so we can see these. Let's see. I see R here in the corner. Its corresponding piece in the image. Ooh, that's nice. R just equals 100 degrees. Not much calculating to do there. I guess we're staying with the color red for a little bit. Okay, the next piece I see is the side R. Ooh, we're going to try this again. Here we go. Side S matches the side with a value of 8, so S equals 8. You get a jump start on the last one here. Find T. T's hidden down below my image. It's the base of that figure, so I'll set that value equal to the base of the pre-image. So 2T equals 10. Use my wonderful algebra skills, and I find that T has a value of 5. So that's one way that we can use the translation postulate. Because we know translations preserve length and angle measure, we can find missing values. Sometimes we like doing more than one translation at once. So when 2 or more transformations are combined to form a single transformation, the result is called a composition of transformations. A composition. A composition of transformations. So lots of transformations, lots of moving our figures around is called a composition. So the composition theorem says that the composition, when we do more than one movement to an image, the composition of 2 or more rigid motions is still a rigid motion. It means the original image and the final image, no matter how many times we move it, are still the same lengths, same angle measures. So here we can see some support for that. So there's an image to the right, some blanks for us to fill in here on the left. So that theorem, the composition theorem, is important because it states that no matter how many rigid motions we perform, lengths and angle measures are going to be preserved in that final image. So, for instance, the composition, what we're focused on, the composition of 2 or more translation is just a single translation. So if we're just working with translations, just the slides, we can slide the image around as many times as we want. But there's always a way we could have just written the original pre-image and the final image in one fell swoop. So I'm going to zoom in on this picture to show you what I mean. Here it tells us this blue pre-image is translated. It's moved along the vector and becomes this red image. And then someone decided, let's move that red figure again. So they used another vector and moved it. And now we have a green segment. You can see there it's P double prime, Q double prime. You'll notice that that notation increased because we moved the original image a second time. But the composition theorem says instead of doing the work of moving it over here, we could have found a vector that just moved us from pre-image to image in one single move. So what we're going to do is look here at an example. We have to describe the translations that are happening. We're going to list every step of the way, and then we're going to see if we can combine them into a composite translation. So here in our graph, we're going to start at the blue pre-image. So it's looking like it's called segment SR. You can see that right here, SR. We need to know how that moves and becomes the red segment, S prime, R prime. So I'm going to write in red since that's what we're trying to get to. So I'm going to use my bunny hop method. They've already set me up for rule form, which means I know I have to start with X and Y in there. We're going to add and subtract our changes. So here we go. How does S become S prime? I'm going to start with my horizontal. So 1, 2, 3, 4, 5. So we added 5 here. And then how many did we go down? 1, 2. So we went down, which is subtraction, 2. Down 2. If I need to check, I can use point R to R prime, and we should find the same values of right 5, down 2. So now we're going to find the second translation. How did this red segment become the green segment? So I'm going to use my bunny hop system again, remembering in rule form, I still have my X and Y set up for me. So here we go. S prime to S double prime. We're going -1, -2, -3, -4. We went left 4, so that's a negative. And then we're going down 1 and 2, so -2 again. And so now we're going to try and see if it's possible. Could we have just moved from this original pre-image in blue, segment SR, to the final image, the green, S double prime, R double prime? So I've got 2 ways to do that. 2 ways to do that. I'm going to show you the bunny hops first because that's what a lot of us are comfortable with. It looks like we just bunny hopped right 1. So X plus 1. And then let's bunny hop down. So we're going down 1, -2, -3, -4. So Y minus 4. So if bunny hops are the easiest way, stick with that method. Graph those things, count. Super easy. If you're more algebra brained, you might see here that we can add these two together to get the result. What's 5 minus 4? It gave us +1. What's -2 minus 2 more? -4. So if you're algebra brained, absolutely feel free to find the translations individually and then use algebra to put them together for the composite. Or if you want to go a little quicker, maybe just go from your original to your final image when it's possible.
So hopefully you have a better understanding of translation. Maybe you'll even start to see translation in your regular life, like when you translate to the restroom, or when you translate your hand to ask a question, or when you say to someone at dinner, "Translate the ketchup here, please." Math is everywhere.